Chance to shape your future is here. Learn and connect with exciting new opportunities. Are you ready for the next step?
Okay, good afternoon, everyone. Let me just share my screen. Okay, so my name is Dr. Roger Giddings. So I'm from the DSP Centre of Excellence at Bangor University, and my presentation this afternoon is to give you an overview of the DSP Centre and to talk about some of the emerging technologies we're working on. So DSP stands for Digital Signal Processing, and I'll be explaining a bit more about what DSP is in my talk if you're unfamiliar with DSP. So the DSP Centre is a ERDF funded project. So it's a £6 million project with £4 million of funding through the ERDF scheme. Okay, so the overview of my presentation. So I'll start with an overview of the DSP Centre. Then I thought it'd be useful to explain a little bit about what exactly DSP is, and then I'll look into the emerging technologies that we're working on. So first of all, an overview of the DSP Centre. So we're based at Bangor University's Science Park, known as MSpark. So why have a DSP Centre in the first place? Well, DSP can be considered as sort of the brain of modern technologies, especially sort of ICT technologies. So it's the digital integrated circuit-based process of analysing and modifying signals to enhance the performance of signal-associated functions and deliver new intelligent functions. But I'll be going into a bit more detail later on to give you a better idea of exactly what DSP is. DSP is also one of the key driving forces behind 5G technologies and beyond. I mean, it's one of the key driving forces in sort of 4G at the moment as well. But 5G will ultimately transform communications. It's going to drive efficiency and productivity, and that's going to enable the what's known as the fourth industrial revolution. So as far as we know, there's no research centres dedicated to addressing the sort of the DSP challenges for 5G and beyond systems. Now, the Optical Communications Research Group at Bangor University has already established a strong basis of DSP-based research, and we've been around since far back as about 2006, and we've already captured lots of funding. We've captured about £12 million over 30 projects. We've published over 450 papers in high quality journals and conferences. We've filed 8 patents, and we've also got a good experience of working or collaborating with industrial and academic partners worldwide. So what is the research focus of our DSP Centre? Well, the key focus is on DSP-enabled optical communication systems to support future fixed and mobile networks, and in particular, we focus on 5G and sort of associated 5G ecosystems. So we make use of Bangor's already established DSP research capability, and also by working with a large number of partners, we've got actually a well-balanced and what we call a skill complementary expertise, you know, from both global leading industrial partners and also Welsh and UK partners. So we cover the whole spectrum of you know, expertise that is needed. The research areas we're looking into, sort of the different areas are, first of all, the DSP algorithm design and optimization themselves. So with the the different algorithms, that you need to design them and optimize them. But then the next areas we look at how we use those algorithms, in the flexible transceivers and networking devices that you need in order to build your networks. Another area is the convergence of optical and wireless transmission systems. So currently the fixed network and the wireless networks, they've been developed independently, but we believe if you can merge those two networks together, there's huge advantages from that. And one of the concepts we've come up with is the idea of what we're calling a cloud network architecture, where the network, you can just consider it as a cloud, and you can then sort of dynamically control the connectivity in that network, to meet your existing user traffic demands, and you can just change it on the fly to meet your network requirements. Another area that we're focusing on is what is called software-defined networking. So this is a new technology which has emerged in recent years, and it's a technology that allows you give you much more flexible control of your network, because it decouples the control plane of your network from the data plane of your network, giving you much more flexibility in how you can control your network. And also we want to build a 5G test bed, so we can actually test our technologies in a real environment, and then through extensive field trials. So in terms of our resources, I think there's something going wrong there. We have, in terms of staff, we have 11 researchers. We have 9 academic staff from the university, and then we also have visiting researchers from industry and academia. We've just had a couple of researchers return back to their home countries recently, but also, having visiting researchers is a bit difficult in the current situation we're in. We also have an improved research lab, so it's worth about £2.5 million. We've got very state-of-the-art equipment. We can work with frequencies up to over 40 gigahertz, all the way from sort of very low frequencies all the way up to 40 gigahertz. We've got a real-time DSP test bed, so we can actually test the algorithms in real time. And we've also got rigorously verified comprehensive simulation platform, so we can do sort of software-based analysis of the DSP algorithms and the systems. And then through our partnerships in the centre, we've got well-balanced and skill complementary expertise from our both global leading industrial partners, and also our Welsh and UK SME partners, and also we have partnerships with universities worldwide. So these are the partners in the DSP Centre. So we've got a total of 28 industrial and academic partners. So they range from network and service providers, component manufacturers, software developers. We've got 2 large end users, Airbus, TWI, they're both based in Wales. We've got 6 equipment and system vendors, and we've also got a number of universities. So what are the requirements of the DSP Centre funding is that we attract more funding into the centre. So we've got a number of areas where we're trying to attract more funding at the moment. So the first one is what we're calling the national strategy project. So this is quite a big project. It's about £25 million project over about 5 years. And this has 3 elements to it. So we've got the research part. So we want to significantly expand the research capability. And we're hoping to get around about 50 full-time researchers eventually. Second element is to address the sector's skills shortages. But we want to establish what we're calling a DSP college. So this will cover both postgraduate courses and sort of high-level technician courses that will address the skills we need for these DSP-based industry. And then the third part is that we also want to commercialize the technologies that we're working on. We want to develop, we want to have a spin-out company, and we want to, we want to see products coming out of our centre eventually, which are, we can also say that these are products which are made in Wales. So the next project, which we're currently trying to put together, is a 5G rural test bed. So this is its estimated budget of around £9 million over 2 years. So the idea is that we establish North Wales 5G rural test bed. So that will incorporate the DSP Centre developed technologies. And we're looking at delivering 3 5G use cases at the moment. So the first one is just basic rural broadband connectivity. The second one is in the area of healthcare, and then also we're also looking at the use case of surveillance. So we want to conduct field trials for the purpose of providing local residential and commercial customers and SMEs with gigabit capable fixed and or mobile broadband coverage, so super fast broadband connectivity. We want to provide targeted organisations, with these defined 5G use cases. So that's something we'll need to do. We'll need to try and engage with suitable organisations we can work with on these use cases. We want to explore the feasibility of implementing the 5G demonstrated test bed, over a wider geographical area of North Wales and sort of a variety of topological environments. So we can look at how we could how feasible it would be to then expand the test bed to a wider area. And also when we've tested these technologies in the test bed, we want to explore how feasible it is to then commercialize these technologies. And then finally, we want to propose a new operation model that will be capable of cost effectively extending the rural super fast coverage, in order to address the North Wales digital connectivity strategy. So the partners in this rural test bed consortium, so there's Bangor University, so that's us, the DSP Centre, Vodafone, so a mobile operator, Fibre Speed, so they're a fibre network operator with a network right across the North Wales. Comtech, Sorrento Networks, they are a network equipment vendor. Photech, so they're a company which work with distributed fibre optic sensing technologies. So that's something we're hoping to incorporate into the test bed. And then ITS, who are a wireless and fibre infrastructure provider. The areas we're looking at covering with the test bed, we're looking at areas which have a sort of poor broadband coverage at the moment. So we're looking at the area around Holy Island and around Llangefni, and particularly Holy Island area is good because of the obviously there's the port there, so we can maybe support some functions there needed by the port. And the last one I want to mention is the North Wales growth deal. So we have a bid in the North Wales growth deal for £3 million. So the idea here is that we could significantly extend the research infrastructure capacity and capability. So and this would allow us to generate the microwave signals for all the the proposed 5G frequencies, because with 5G they're looking at using some fairly high frequencies. We want to strengthen the DSP Centre's research and funding capture capability. We want to significantly accelerate the commercialization of the DSP Centre developed technologies. And also, we want to maximize the DSP center's impact to the whole wider economy. We want to see it helping to create jobs and so on in the region. Okay, so next I thought I'd just explain what is digital signal processing. If you're a bit puzzled exactly what it means. So there's a number of different ways we can use DSP. So the first way is to process and modify real-world signals. So what we need to do is first of all, we need to take our analog real-world signal. That could be an audio signal or a video signal, for example, and then we need to convert that into our digital signal. So we need a device called an analog digital converter, and this basically takes regular samples of our analog signal to give us our digital samples. And this is basically a sequence of numbers, of digital values. We can then apply our signal processing to this digital signal, and this could be in software or hardware if you need to do it in high speed. And we generate a new digital signal, and then we can convert that digital signal back again into an analog signal using a digital to analog converter, and then we get a new analog signal. So we've taken a real-world signal and we've processed it, and we've generated a new analog signal. So a couple of examples of this. So in audio signal processing, this could be an example is real-time noise cancellation, or in image processing, an example is like real-time augmented reality. Another way we can use the DSP is in the analysis of real-world signals. So again, we take our real-world signal, which is always an analog signal, we convert that to our digital signal, and then we can apply the signal processing. But then we're trying to extract some information from that signal to then feed into another software application. So a good example of this is speech recognition. Yeah, so you're all familiar with Siri and Alexa. So that is basically being achieved through DSP. Other examples are image analysis, such as number plate recognition, and also face recognition, which is becoming more popular now. Okay, and then the third way of using DSP is basically how we use DSP in our research is in the application in advanced communication systems. So basically what we do is we take the incoming information signal, which is already digital information, and then we put it through the digital signal processing to generate a signal that we're going to then transmit through our communication link. So we convert that digital signal into an analog signal, which is suitable to then go through the communication link. It could be a radio link or an optical fiber link. And then at the receiver side, we receive the signal. We need to then convert it back to a digital signal so we can then process it and recover the data. Now, we've got the DSP there in our system, so we're using that we can generate complex modulations to give us good performance of our link. But there's also a lot more we can do with the DSP. We can compensate for transmission path and component induced distortions. We can do signal multiplexing, demultiplexing, so we can share the channel between users. We can do things like increase the spectral efficiency, so we get higher throughput in a given bandwidth. We can dynamically change the signal characteristics. So we can change the bandwidth of our signal and the bit rate. So depending on what sort of bit rate you need, we can dynamically control that. We can also do things like power management, so we can control the power consumption of the transceivers. And basically we can achieve highly adaptive, reconfigurable optical and microwave transceivers. And also one thing we can also do with the DSPs, we can implement physical layer data security, which is becoming more and more important. So I'd now like to go through some of the emerging technologies. So I'm going to look at the idea of DSP-based access networks. Then I'll look at the idea of distributed fiber optic sensing. Then I'll talk about physical layer network security, and finally talk about high performance virtual networks. But before we look at the idea of the DSP-based optical access network, I just want to go through the requirements of future optical networks, to see, why do we need these more advanced optical access networks? Why do we need the DSP? Well, we need significantly increased peak data rates, but we've got to achieve that at low cost and low power. So that is very challenging, because the problem is we can't, people are going to want sort of gigabits connectivity speeds in the future, but we can't just give people gigabit speed connectivity all the time. So what we need is we need to provide dynamic bandwidth allocation, so we can only allocate the bandwidth to people as and when they need it, to make we can then make better use of the network. We need highly adaptive networks to support the widely varying data traffic characteristics. So now the type of data traffic going through the networks can be varying from, there's a lot of video centric data, but there's also now, through the Internet of Things, there's lots of sort of sensor data. So the characteristics can be widely varying. We need to be able to use the network resources very efficiently. We need to support the software-defined networking, which I previously mentioned. We believe we need SDN control all the way down to the physical layer, and this is something that we've been working on. We need low latency networks. The latency is basically the delay through the network. A good example of this would be sort of a remote surgeon. You don't want any delay between the surgeon moving his scalpel at one end and the scalpel on the robot side moving. Also, one thing that is needed in the future is a massive device counts. So with 5G, they're saying we're going to need, we're going to have lots and lots of more users connecting. Also, with, for example, Internet of Things, we're going to have lots of sort of devices connecting to the network as well. So the number of devices and users connected to the network could be growing massively. Then we also need data security right down to the physical layer, and also in the sort of just the infrastructure level. So we need a DSP-based transceiver. So I thought I'd just show you the main elements inside the transceiver. So on the left, we've got the transmitter. So here, our digital data is coming in. It goes through the DSP function, where we put it, generate the signal that we want to transmit. We then have our digital analog converter to generate the analog signal. We then need an amplifier to suitably amplify the signal. And then we have our electrical to optical converter. And then we need to do the reverse operation in the receiver side. Now the idea here is that we can keep the optical link nice and simple and low cost, and we can compensate for any deficiencies in the link, any distortion and so on with our DSP. Okay, so the first DSP-based optical access network I want to talk about is called an optical orthogonal frequency division multiplexing passive optical network. Now, the passive optical network is like the most common way of implementing the access network, the optical access network. So PON means passive optical network. It means you don't have any active devices in the distribution network. So on the left-hand side, we've got the user terminals, and on the right-hand side, this is the equipment at the operator's side. And we've got our DSP, we've got our digital analog converter, we've got our intensity modulator to generate the optical signal. Now, the modulation used here is optical frequency division multiplexing, which is a multi-carrier modulation. And if you look at the diagram in the lower right-hand side, you can see that it consists of a number of equally spaced carrier frequencies. Now, each of these individual carriers can be modulated separately, so we can adaptively modulate them. And also, you can see that the spectra is overlapping, which makes it gives it a very good spectral efficiency. So we're using this spectrum extremely efficiently. Now the thing is, each of these equipment at the user's end, it can generate all of these subcarriers to fill up all of the available spectrum. But by turning the subcarriers on and off, we can just use part of the spectrum. So this example spectrum here is showing that we're equally dividing the spectrum between all of the 4 end users. But by turning the subcarriers on and off, we can then change the allocation of the spectrum, and therefore the bandwidth and the bit rate. We can dynamically change that allocation amongst the end users. And through doing this, we can actually get a very fine granularity to the bandwidth allocation. And another advantage of this type of modulation is that it's highly tolerant to the optical transmission link and the component-induced distortions. Now this OFDM is actually a very successful modulation format used in radio systems. It's used in Wi-Fi, 4G, 5G. There's many examples, but we were the first group in the world to demonstrate this type of modulation technique being used in an optical link in real time. So we had real-time digital electronics processing the signals. So we demonstrated that we get a capacity of around 30 gigabit per second on a single wavelength. Now with conventional technologies, or the standards, they run up to 10 gigabit per second on a single wavelength. So the next technique for the access network, which is using the DSP, is what we've called digital filter multiple access. Now this is basically a multiplexing technique, which is enabled by the DSP. The format of the signal that you send it can be anything you like, basically, but the DSP allows you to multiplex these signals onto a single fiber. So it allows you to share this fiber in a very dynamic way. So the encoded data, it's up to you how you encode the data. You could actually use different types of modulation format. But here what we're doing is we're using digital filters in order to control the bandwidth and the spectral position of our signals from each of the end users. So again, here, if you look at the spectrum of the whole system, we've equally distributed the bandwidth. But again, by reconfiguring the filters on the fly, we can control how much of the bandwidth each of the end users gets. So we can dynamically allocate the bandwidth as needed. But in the receiver side at the operator's premises, what we need then is we need a filter and then the decoding DSP to recover each of the separate end users' signals. So we need sort of quite a bit of DSP here to recover all the individual signals. But this achieves huge flexibility in the use of the access network bandwidth. So just by simply reconfiguring the coefficients in these filters, which the coefficients are just stored in memory, they can be rapidly, instantaneously changed. You can change the characteristics of your filter, so you can therefore change the bandwidth allocation given to each end user. Okay, and again, we were the first group in the world to demonstrate this type of network operating all in real time. So the last one that I'd like to present is called a hybrid OFDM DFMA PON. So this is actually, as you could guess from the name, it's a combination of the last two PONs that I presented. So here we've got the filters doing the multiplexing, but we're using the OFDM for the signal modulation. So but what that allows us to do then is we can drastically reduce the complexity of the DSP we need in the receiver side. So if you can see here, we don't need all these banks of filters. We don't need one filter for each end user. So we can actually recover all of the subcarriers from all of the end users all at the same time. So this drastically simplifies the complexity of the DSP, so that saves cost, and it can also reduce the power consumption, which is also extremely important. So we can also, this will reduce the complexity on the transmitter side, because now we don't need to make the each end user be able to generate subcarriers across the whole of the frequency band. We can limit that to, we can have a maximum bandwidth, and then it only needs to generate subcarriers to cover that maximum bandwidth. So this also, compared to the DFMA PON using OFDM signals, we actually found we got better performance with this hybrid technique. We also found that it relaxes the signal timing synchronization requirements, so it's much easier to synchronize everything in the receiver side. And also it's possible to use this technique in the downstream direction as well, so for the data going from the network operator down to the end user. So this, we can actually use a similar technique in both directions. Okay, so that was the new advanced technologies based on DSP for access networks, optical access networks. So then I'd like to just look at some other technologies we're working on. So the first one is distributed fiber optic sensing. So the idea here is that you're using the fiber as a sensor. So you can think of the fiber as acting as a continuous line of microphones. So any disturbance to any part of the fiber can then be picked up. So, but there's existing systems, commercial systems available which perform this task, which can use as distributed fiber sensors, but they need their own dedicated fiber in order to work. So what we're looking at is how we can use the same fiber to simultaneously carry data and also act as a distributed sensor. Now you can imagine if we can do that, then all of the fibers which are out there in the communication network, they can just be turned into a sensor as well. So then you can have a mass rollout of these distributed fiber optic sensors. Now we use advanced DSP algorithms. What they do is they process the back reflected light, which is affected by the fiber disturbances. So when as the light travels through the fiber, we actually get back reflections. They're quite weak, and they're affected by the physical disturbances on the fiber. And we can detect those back reflected signals, process them, and we can work out, where the disturbance was, what was the frequency of the disturbance, and so on. And we can also then we can optimize the algorithms, depending on the application of the fiber sensor. Now, these are the distributed fiber optic sensing is applicable to infrastructure integrity monitoring, but also it can be used for the optical network infrastructure security itself. So, okay, so for example, one infrastructure integrity monitoring example is pipeline integrity. So if you've got a fiber running along the length of a pipeline, any disturbance to the ground, or if you start to get a crack developing, you're going to get some vibrations which can be picked up. So you can then hopefully you can prevent a disastrous leakage from the pipe. Another application is traffic flow monitoring. So if the fibers are installed alongside a road, you can pick up the vibrations from the traffic. So you can very easily monitor how the flow of the traffic, is it flowing nicely or is it all stationary? So you can then monitor the state of the traffic and use that to build a traffic management system. Another example is if your fiber is running alongside of a rail track, then you can pick up the vibrations when the train passes. And if you start to pick up some abnormal vibrations, that's an indication that there could be a malfunction of the rail somewhere, so you can then go out and you can, you know, fix the problem before you get some drastic problem with the rail. But the other big advantage of this technology is that we can actually monitor or secure the infrastructure security itself, in the optical network infrastructure security. So if somebody wants to attack your network, you know, or even they're digging up the road and they're getting close to your fiber, you can detect that somebody's getting close to your fiber, and then you can go and prevent it. So the next technology is physical layer security. So the idea with this technology is that, so in your optical link, you have your optical transceivers at either end, and you're sending your optical signal through the fiber. Now, current systems send optical pulses, so sort of square pulses. Now, we then pass the signal through a DSP-based physical encryption unit, which then basically physically changes the signal. So if you look at the signal going through the fiber, it no longer looks like a series of square pulses. It basically looks like a noise signal. But then we have the decryption unit at the receiver side, which will then turn that back into the original data signal. And now in these two units work as a pair. So the receiver, the decryption unit, it knows how the encryption unit has encrypted the signal. So if somebody tries to tap into your signal through eavesdropping, you know, they want to capture your data. And this can be done quite easily. I mean, there's a number of methods, but one way is to just bend the fiber until some of the light escapes, and then you can pick up that light. But if you then detect that with a optical detector, you know, you're basically just going to see this encoded signal. You're not going to be able to pick out, you just can't recover the ones and the zeros. So you can't get to the data. Now, the existing physical layer security systems, they now employ sort of quantum techniques or chaos-based techniques, but these are very costly and challenging to implement. So with our DSP solution, we believe we can build a solution which is going to be low cost, but basically a plug and play system. So you just plug in the units either end, and then your link is secure. So, and then these security devices, you just need to install them at the network edges, so it requires no modifications to the network itself. Okay, so the last technology I want to talk about is what we're calling high performance virtual networks. So in the access network, so we've got the on the right hand side here, we've got the network operator's premises, and on the left hand side, we've got the end user premises. And basically the traffic always flows from the end users to the network operator. So it can be upstream or downstream, but the traffic never flows between the end users transceivers. But by implementing a simple and low-cost modification to the access network, the DSP-based transceivers can achieve direct communication between the end users. So these end users can then talk to each other, and we can actually build high-speed and low latency interconnections between these end users. And this is possible without disturbing the connectivity between the end users and the network operator. So we still get the same performance of the access network of upstream and downstream traffic, but we've also got this inter-user connectivity. So applications of this, so we can build high performance virtual networks between commercial premises. So if you've got, say, several different office blocks, but they're all on the same access network, you can then have a high speed link between your offices. You know, this could be a university campus. If you've got several buildings all on the same access network, you can then build high speed links between the different buildings. You could use it for interconnection of latency sensitive IoT sensors in all in a localized area. So if you've got sensors in a given area, they're all connected to the same access network. You can have high speed, low latency links between the sensors. And also these, so these in the access network, these may not necessarily be end user premises. These could be 5G mobile cell sites. So this could be, the tower in the 5G cell, and then we can have connectivity directly between the 5G cells. So there's a number of applications where this is useful. I mean, just one of them is to be able to control handoff as users move between the cells. Okay, so thank you very much. That's the end of the talk. I think I've left just a few minutes there for questions. Okay, so I can see one question. How does the maximum signal to noise ratio? Oh, sorry. Okay, I can see them now. Also, first question is, what is the maximum ADC sampling rate and bits of resolution that your real-time DSP system can provide? So the real-time system that we developed, so that can work up to 4 gigasample per second, and that's a resolution of 8 bits. So that's and actually the 4 gigasample per second, when we built it, that was sort of one of the highest speeds you could get. But these days you can get ADCs and DACs going up to like 50, 60 gigasample per second. So we're planning to build a higher performance real-time system. Okay, the next question is, how does the maximum signal to noise ratio and bandwidth of your optical microphones compare with a MEMS microphone? That's a very good question. That's not really something we've looked into. But I guess the advantage there is that we're using the fiber itself as a vibration sensor. So even if it may not have such good quality and performance as a MEMS-based microphone, you get the fact that it's a distributed sensor, so it can sense anywhere along the fiber, and then it's it'd just be if you wanted to try and do the same thing with individual microphones, it would just be so expensive compared to just using the fiber that's already there. Okay, so I think that's the end of the questions, and I think I've just got that in the time. So thank you everyone for your attention, and have a good rest of the conference.
Thank you for joining the Emerging Tech Fest. Join us again on our virtual live sessions, or watch us on playback anytime, anywhere.